very detailed mathematical level. And there's a minor risk that you have to deal with the translational tone if you go the first written exam. You know that you have 3 attempts to go to written exam. So if you decided not to do midterm exams, you can go and do final exam, which is a written exam. And you will have 3 attempts to do that. The first attempt, the first exam paper will be easy. I'm asking like, what is your name and what do you like? How is that you like about the course, and what about the weather-wise? Do you like to be in Finland? These kind of questions. And then I'm asking a revolute tone and stuff like that. Second exam, I'm asking translational tone and something that is ugly and difficult. And the third exam is so difficult that I cannot pass by myself. So think about it. You have these 3 choices. So it progressively becomes more and more difficult. All right? So now the next one that I would like to introduce is a translational tone that combines 2 bodies together. So I have here body A. Body A is a beam-like body. This one here. And then I have box-like body, body B. And these bodies are coupled together via translational tone. So it's meaning that the body B can translate, it can slide along the length of body A. It can go back and forth. If the body A rotates, body B will do the same. And again, it can slide along the length of the body A. So that's a translational tone. So you need 2 constraint equations to define the constraints like this. First constraint will be extremely simple. You simply say that, okay, the initial orientation, angle theta, related to body A, and angle theta related to body B, those have to be along with the certain constraints, and that's you basically say that these have to be equal. So that's kind of the idea of your first constraint. Second constraint is a little more complicated because then you kind of prevent the relative motion between the 2 bodies. And we need a little bit of mathematics to make that happen. So that's the next assignment. And before the next assignment, let me check like how is a. Okay, so we have 74 answers. You know, I'm thinking that this time it's going to happen. Guess what? 100% success rate. 100%. Yes, 100%. You ready? So what if it is 100%? So are we going to stop the lecture? No, we're going to make a lecture longer than it is typically, because that's the way we can celebrate it. So we can make this like 4 hours lecture. Yes. So you're with me. Okay, you scared to see the results? No? Not great. Not great. Okay. Okay, so okay. So how should I make the interpretation of this? Is it like I should close it like right now, right here? Or okay. Honestly, a little bit of disappointment. Okay, so let's go back to this. Okay, let's get started from the answers that makes no sense. Okay, the only few ones mentioned that this defines the physical dimension of the body. Nothing to do with that. Absolutely nothing to do with that. Defines a particle in global coordinate system. Not that either. You know, the particle, we define that by using this equation. Not constraint. It's an ingredient inside of the constraint, but the constraint, idea of the constraint is what? Tell the relation between the generalized coordinates. So it's interconnect. It combines the generalized coordinates. That's the assignment of the constraints. So it is saying that, okay, these coordinates are no longer free to move, but they are coupled in a certain way. And that's because of the constraints. So this is a correct answer. Define the body configuration in a global coordinate system. Not really. Not really. But there is a point. There is a there is a little bit of sense in this. Because if we have a system that there is a 0 degrees of freedom, then you can solve the configuration based on the generalized coordinates, constraint equations. Okay, so maybe I will give you a points if you answer the B, A or B. It's still not 100%. Okay, but the correct one is A. Okay. All right, so let's go and practice this, and then I have one more in-class quiz for today, and then we're gonna stop. Okay, my first constraint was the simple one, like I explained. So you're basically saying that the orientation of the bodies have to be same all the time. Same all the time, that meaning that it have to be according to parameter C. C could be equal to 0, so it's meaning that then the orientation of the bodies will be always same. Or they may have a little bit of, angle, initial angle with respect to each other. So that's C there. Initial angle having the numerical value C. Let me explain. So if you have here beam-like body, and then the box-like body is oriented like this. Hold on. This is my body coordinate system. So this angle here is C, telling how much they are separated in a initial configuration. All right? So that's the first constraint. Second constraint is a little bit of headache. In second constraint, I have to introduce several points, and with help of those points, I can define two vectors. And then using the perpendicular condition, mathematical condition, I can actually prevent the relative motion of these bodies. Because the thing is that now the B cannot move this direction without the translation of the body A. So that's what I wanted to constrain. And I can do that by introducing point O, point P, and point Q. Point O will belong to body A, point B and Q, they will belong to body B. Let me give you a better picture. So this is a situation. So I have, I'm introducing kind of like assisting points. This is a first point, and I need to change the color to make this more visible. This is my first point O. This is my second point P, and then I'm introducing one more point Q here. And now I'm defining those points using the method based on, guess what? This one. This equation will be used again. So I'm simply defining this point, and this point by using this technique. And once I have these points, then I'm able to draw the vector that connects these points together. Then I have two vectors, and perpendicular condition of two vectors. What's that? That's if I have vector x multiplied by vector y, that's going to be equal to 0. That's perpendicular condition. All right? That's what I'm going to do. You follow? You're with me? Okay. So let's make it happen. So let's define the point O in the very beginning. The point O, is defined here. So this is point O. So to make that happen, I first have to travel the body reference coordinate system of the body A. All right? So that's this component. Then I'm accounting the orientation of the body A, 2x2 rotation matrix, and the vector U bar. I really don't know what is this numerical values. I don't care this time. So it's just the vector U bar. That's my first point. My second point, which is this one here, P, that belongs to body B. I will define that in a very same way. Again, I'm going to origin of the body B, then I will account the orientation of the body B and the vector U bar. And I don't care what is the numerical values. I don't need to know that this time. This is my first vector. The vector is called K. All right? It connects position, and it connects the body A and B. So it goes from O position to B position. Here to here. Makes sense? Yes, sir.
Shouldn't it be the other way around? BP minus AO? Because I think...
So the direction?
Yeah.
You made it because of the direction?
Yeah.
We could make it in another way around as well. This doesn't really matter. Okay? But, so you say P minus O.
Yeah.
Okay, I need to do the exercise, and I need to show this to you next week, like how we end up to have the same business. Okay? Then H belongs to body B. And the body H is the one that connects the P and Q. So first I will go to origin of the body B. I will account the orientation. A vector U bar takes me to P. And then I will do the same. I will go again, origin of the body B, orientation, and vector U bar. And that's because these guys will be eliminated. This will be what is that it's going to be left. Okay, that's my second vector. And then, once I take this mathematical condition, so it's H multiplied by K, that have to be equal to 0. So I have two vectors, I multiply them together. I'm saying that the results have to be equal to 0. That, by the way, is a scalar component because it's a matrix, vector multiplied by vector. So it's a scalar component that is left. So it's a one equation. Okay, it looks bad, and it is bad. But don't get confused about math. Use a symbolic math tool to solve this for you. Okay, so this is a vector H, this is a vector K, and everything is written down, and finally this is how the K and H look like, and then I simply do the math, and I'm doing a little bit of elimination. This is finally how my constraint reads. I'm using a little bit of simplification in a way, but the big picture is this. So I have two vectors, and I'm imposing the perpendicular condition. That's how I can get the second constraint equation. Makes sense? A little hard. But no worries, it's going to get harder. Soon it's going to be more difficult, way more difficult. Are you coming next week? Maybe. We'll see. Okay. Okay, so what do you guys say if I leave this without further details? Are you comfortable with this? Okay. So with what are the simplifications that I did there? I mentioned, I know that this is actually in origin of the body reference coordinate system, so it allows me to use this substitution. So vector U bar associated to this point will be having 0 values, and the P is also located in the center of the body coordinate system, so I can use these values here as well. And this is how the Q is located with respect to body x-coordinate axis. So those are the simplifications that I'm able to do. And when I substitute these simplifications, this is what is left. This is my final constraint equation. Very mechanical math, nothing else. Okay. Then let's practice this. So I have two bodies that can move with respect to each other. So there is a body A and body B, and they are constrained in such the way that the body A is constrained to ground via revolute joint, and then the body A and the B are constrained together via revolute joint in a point P, and then here point Q I have primitive joint. The primitive joint prevents the motion of this particular point Q in a global y direction. So it cannot travel to that direction. Okay? What's the number of degrees of freedom? So I have two moving bodies, so it's going to be what? 6 generalized coordinates. How many constraints I have? So it's going to be 2. How many revolute joint? 1, 2, and the primitive joint. So it's 1. Okay, 1 degrees of freedom. Okay, so let's calculate the constraints for this system. So let's get started from the first body. So let's first define the constraints that is associated to this point here. And now there's a big temptation that we can take a shortcut, because we're here in the very beginning. So we are in the origin of the global coordinate system when we get started in this assignment. and the constraint is imposed to this very same location. So can we make a shortcut and explain this position, without traveling to body reference coordinate system? No. So we always have to go to body reference coordinate system. If you're going to take a shortcut, it's like a criminal action. Not allowed. So you can do whatever you want, but never ever shortcut. You always have to go first to here, which is a body reference coordinate system, and then you come back. That's the way it goes. Always the body reference coordinate system, and then wherever you wanted to go within the body, no matter where they are located. Don't think about don't try to be smart. Don't try to make the shortcuts. They will not help you at all. Okay? So I first travel to body reference coordinate system, which is defined by this vector here. Then I will account the orientation of the body reference coordinate system by 2x2 rotation matrix. All right? Then I'm now here, and in this coordinate system, and I have to go back to the origin of the global coordinate system, which is the point O. How can I make it happen? Well, with help of vector u-bar, I have to travel minus L divided by 2. Minus because if you take a close look about this one here, x-axis is pointing this direction. And I have to travel from here to here. So that's why the minus L divided by 2. Y direction, how much I have to travel this direction? 0. What's going to be my constraint? How can I say that this point O have to stay in origin of the global coordinate system no matter what? It goes in such the way that I say that this equation have to be equal to 0, 0. Make sense? Okay, good. Okay, that gives me two constraint equations, 1 and 2. All right? Then I'm ready to move on to second one. So this time I will define the point P by using the body A, and I will do the same by using the body B. I'm simply putting these notations to be equal. That's going to be third and fourth constraint equations. And again, how can I make this happen? Again, I'm following this very familiar equation. So first, traveling the body reference coordinate system, then I will account its orientation, and then with help of vector u-bar, I go wherever I need to go. Right? Makes sense? Okay, so this is body A definition, orientation of body A. Vector u-bar, this time is L divided by 2 positive direction. Y direction is equal to 0. Then I will do the same with respect to body B. So I will go first here, then I will account the orientation of body B, and then with help of vector u-bar, I will call this point B. Right? Vector u-bar will be minus L divided by 2, 0. That gives me third and fourth constraint equations. Clear? Nice. So then, final one. The final one is related to point Q, and the point Q is actually located in the axis of 0 y-axis. So I'm simply defining this point here, and then I'm saying, okay, the motion in a global y direction have to be equal to 0. So first I'm traveling the body reference coordinate system of vector of body B. Then I will account the orientation of body B, and then I will go to this point Q with help of vector u-bar. It's going to be L divided by 2, 0. And then I'm saying that this y component, this component here, have to be equal to 0. It cannot move in a global y direction. You got it? So I will take this component, this matrix multiplied by this column, this row multiplied by this vector. That gives me fifth constraint equation. Nice. Okay. So what it is? So we have 8 minutes time, and it's not going to be enough to open the completely new topic, which is a Jacobian matrix and kinematic analysis. But shortly, what to expect to see next week. Okay. So, kinematic analysis. So you can carry out the kinematic analysis if you have, if you have system that have 0 degrees of freedom. So what it means. So if I have, say, hold on, a pendulum. Pendulum as it is in this configuration have how many degrees of freedom? So how many bodies? I have one body, 1 revolution, 1 degree. Okay, so it have 1 degree in this configuration. Then I'm coming and say, okay, this 1 degree is not free to move as it wants. And it could be the way that I come and say, okay, this angle theta have to follow the equation that could be, say, theta is equal to sine time. So then the body will follow this driven constraint. So that's one additional constraint. So then I have 3 constraint equations, 3 unknowns. Remember that generalized coordinates are equal to unknowns. So those are the things we wanted to solve because they will tell us the configuration of the system. But we have all the information because we have 3 equations, 3 unknowns. So it means that we have a set of nonlinear equations and we have to solve it. How is it we can solve a set of nonlinear algebraic equations? You learned it already in junior high school. Think about it. You have a set of nonlinear algebraic equations. You have to solve it numerically. How you can make it happen? Any guesses? Okay, so you learned it in high school, not the junior high school, but the high school. Okay, you learned it in first class in mathematics in a university. So there are these iterative methods, many different methods that can be used. Have you ever heard the methods called Newton-Raphson Method? Yeah, that is that we can use. So we can use that using an iterative method of Newton-Raphson. So it tells us a solution in a position level, and then we also have to solve the velocity and acceleration. All that is hidden to constraints. All that information is inside of the constraint equations. We just use a little bit of mathematical manipulation, and then we can solve it. Okay. All right. So the kinematic analysis goes, and that's the way that we're first going to carry out the position analysis. Position analysis is a little bit challenging because we have to use these iterative methods, Newton-Raphson or others, but we're going to use Newton-Raphson. And with a certain number of iterations, we can get the position, accurate definition of position at a certain time. Once we have position, then we can solve the velocities and acceleration. And that's the idea. That's how the whole procedure goes. You have to take care of all these stages, but step 1 is critical. Step 1 is the most difficult position level. And to make that happen, you have to write down the constraint equations, and pretty much that's all you need. Okay, so once you have constraints, everything is rest is downhill. That's what it means. Boilerplate. Okay, this is a very heavy math, so we are not getting involved to that too much today. So 4 minutes, and we have. Okay, we can close for today. And then next week we will get back to this, and I will teach you something that is called Newton-Raphson Method. And in Newton-Raphson Method, there is something extremely, very, very critical to learn, and that's Jacobian matrix. That's what we need to learn to find out what's the direction, how is that we can update the generalized coordinates to find the position or solution for position level. Okay. That's all for today. And this Wednesday stuff, I will ask John to send some information to you guys regarding the tutorials on Wednesday. But as what John mentioned, there will be a tutorial this Wednesday. But check out your emails. Okay? All right, and I'm going to close the recording and streaming.